Bismillahirrahmanirrahim. Assalamualaikum and hello everyone. Let's continue from the previous session. So let's look at how to calculate the average power. So if you have a sinusoid signal like this, so for example the equation is Vm sine omega 1t. So this is omega 1. So omega equivalent to 2 pi f, or it is equal to 2 pi over t, in which t is the fundamental period of one cycle. So P average can be calculated by dividing V RMS squared divided by R. So this is equal to V RMS squared divided by R. So what is VRMS? VRMS is equal to V maximum divided by Z2 squared. So V maximum is equivalent to V peak. So this is V max or V peak divided by Z2 squared divided by R. If R is not given, so we can assume R equal to 1, normalized resistance. So P average is equal to Vm squared divided by 2, in which Pm is equal to V peak squared divided by 2. Okay, let's look at the Parseval's theorem, in which it stated that the average power of the periodic signal is actually the sum of the average power in its harmonic components. So basically a periodic signal carries a fixed finite average power. So if you have a periodic signal, for example like this, so it basically carries fixed finite average power. So we can use Parseval's theorem to calculate the average power by considering each of the components. So this is the Parseval's theorem equation, in which P average is equivalent to the square of each magnitude of the components or the coefficients of your spectrum. So the equation can be simplified by P average equal to Cn squared, the magnitude of your coefficients, and n depending on number of harmonics. Okay, let's recap the equation for the exponential Fourier series, in which the signal Vt equal to C naught plus the summation of Cn, Ej, and omega naught t. Okay, so to calculate the P average or average power, you need to consider the coefficients for each of the pulses up to the number harmonics required. Okay, so in this case, you have the C naught, P average equal to C naught squared plus C1 squared plus C2 squared plus C3 squared, and also the negative frequency as well. Okay, so the equation can be simplified by adding the C0 squared plus 2 times Cn squared. Why we have 2 here? Because if you notice that the amplitude at f1 and f minus 1 is the same, so you can just simply calculate the power at C1, so multiply with 2, representing the negative frequency as well. The previous example, in the previous session, example 2, we have the final answer of this spectrum. So how to calculate the P average? So you need to consider the coefficients of each of the pulses, both at positive and negative frequencies. So in this case, P average is equal to C naught plus C naught squared plus 2 times the Cn squared. Okay, so let's start with C naught. So C naught is 3 squared plus 2 times C1 squared. This is your C1. So it's 3 over pi squared multiplied with 2. So move on to the next one. 1 over 5, 1.5 divided by pi squared multiplied with 2 for the frequency at 4 and minus 4. And lastly, 1 over pi squared multiplied with 2. So total them up, then you get the average power for the signal. Okay, now let's look at the analysis of Fourier series in a circuit. So we're going to discuss on passive components in a circuit, including resistor, inductor, and capacitor. Okay, let's have a quick recap in circuit theory. When you have a simple circuit like this, so the voltage equation is equal to Vt multiplied with current, It, and the impedance, in this case capacitor. So the capacitor is equivalent to 1 over j omega c, and in Fourier series the omega will be different by different harmonic number. So for example, if you have the first harmonic, so it is omega 1. So if you have second harmonic, you have omega 2. So the value of omega 1 usually is not equal to omega 2, omega 3, and so on. So if you have an inductor inside a circuit, so V is equal to I, the current, multiplied with the inductor. So in this case, if you have an inductor, so XL is equal to J omega and L. L is the inductance, so omega n is the frequency at respective harmonic number. Okay, if you have 3 harmonics, so you need to consider omega 1, omega 2, and omega 3. Okay, lastly, when you have the resistor inside the circuit, so V equal to I R. So in this case, in this case, you don't have to consider the omega. Okay, when you have a combinations of more than one passive components inside a circuit, so you need to consider the orientation of the component, whether it is oriented in series or in parallel. So for example, in this case, you have the resistor in series with the inductor. So the total capacitance, the total inductance Z is equal to R plus XL. So again, XL equal to J omega N L. So in Fourier series, you really need to consider the omega n, the number of harmonics involved in the equation. Same goes to when you have a combination of resistor and capacitor. So the total impedance is equal to R plus XC, and XC is given by 1 over J omega n C. Okay, let's have a quick revision on how to write down the mathematical expression of the given signal in Fourier series. So basically, you need to refer to the Fourier coefficients table, look at the closest shape to the given signal, and then you need to identify the parameter involved, for example, x0 and t0. And then you need to notice the first coefficients, the Cn, and also the remarks. So in this case, if you compare the given signal and the table, so it is basically in square wave or square shape. So x0 is equal to Then don't forget to look at the unit, it's millivolt, and then the T naught is equal to 2 millisecond. Okay, 2 millisecond. So you can calculate the omega naught, which is equal to 2 pi f, or it is equal to 2 pi over T. So in this case, the omega is equal to 1000 pi radian per second. Next, you need to use the general equation for complex exponential Fourier series, in which it is the addition of C naught, the coefficients at 0, plus the Cn Ejn omega t. So your omega here is 1000 pi radian per second. So n is the harmonics number, so you need to consider up to the number of harmonics required in a system. So in this case, then you replace all the values you have. So for example, C naught here is 0. So C naught is 0 here. And then Cn being replaced by this equation, negative j 2x naught pi n divided by pi n, Ejn 1000 pi t. So next you need to calculate the Cn. Okay, so assume that the system works up to third harmonics. So you need to consider the n equal to 1 and 3, because if you look at the remark, Cn will be 0 if n even, so you don't have to consider n equal to 2 or negative 2. So this is a Cn, so replace all the values in, so negative j 2x naught, your x naught is 10 milli, and then divided by pi n, in this case for n equal to 1, and this is for n equal to minus 1. Okay, same goes to the third harmonics, n equal to 3 and n equal to minus 3. So this is your x naught. So this is from the equation. So this is the final answer. Okay, next you need to compile them up. Okay, so Vt equal to your C naught is 0. So C naught is 0 plus C1. So this is from your C1. C1 Ej 1 omega t. So in this case, omega is 1000 pi. And then you have j underneath here. Okay, if you want to use cosine signal, cosine function, you can change this minus j equal to e minus j pi over 2. So in this case, since I want to get the sine equation, so you can just leave j at the bottom. Okay, why? Because if you still remember, for sine function, sine, for example, theta t is equal to the Euler's theorem, Ej theta t minus E minus j theta t divided by 2j. So you can have the j at the bottom. So and then compile all Cn values. So this is for C minus 1, and then Ej minus 1 omega t. This is for C3, and this is for C minus 3. Okay, and then to get the complex exponential into the trigonometric form, so you need to use the Euler's theorem. So in this case, you have grouped the same coefficients, so you group the same coefficient. So then this one divided by 2, so multiply here by 2, so you get 40 over pi. And if you have 2j, so it becomes sine function. Okay, same goes to when the n equal to 3 n minus 3. Okay, let's look at this example when you have only one passive component in the circuit. So you need to determine the trigonometric Fourier series for IT. So given is the VT, so you need to get the exponential Fourier series for VT, and then get the trigonometric equation, then you can solve for IT. Okay, so in this case, R equal to 10 ohm. So VT as calculated earlier in previous slide, so given by this equation, so I is basically equal to V divided by R. Okay, so in this case, you have V1T plus V3T. So I is basically equal to V1T divided by R plus V3T divided by R. Okay, if the question asks for more harmonics, then you need to consider more harmonics. So in this case, it is millivolt. So what is V13? V1T is this one divided by R. So 40 divided by, so R equal to 10. So this is your R. And this is 40 over 3 pi divided by 10. So this is your Fourier series, trigonometric Fourier series for the current flow in the given circuit. Okay, let's look at another example. In this case, you have the inductor in a circuit. So same step as earlier. So you are given the Vt in sine function, in trigonometric function. So you need to write down the trigonometric equation of the current IT. Okay, so let's look at the next page for derivation. Okay, so the first step, you need to consider the components of Vt. So in which Vt you have, in this case, three main components. So the first one is V1T when the omega is equal to 1000 pi multiplied with the first harmonics. So this is omega naught multiplied with the third harmonics, and so on. Okay, so these are the main components of your Vt. So next you need to consider the impedance. In this case, you have an inductor given by X and L, and represent the number of harmonics. Okay, so XL equal to J omega L. So if you change the complex number into polar form, so you get J is equivalent to 90 degree. So omega depending on your harmonics number. Okay, so let's look at this calculation. When you have n equal to 1, so if you have n equal to 1, so your J omega 1 L equal to, so this is omega 1 L, so omega 1 is 1000 pi, and your L is 0.1, and then J equivalent to 90 degree. Okay, same step for n equal to 3, 5, and so on. Okay, so to calculate IT is equivalent to V divided by XL. So in this case, assume you need to consider up to third harmonic. So consider n equal to 1 and n equal to 3. Okay, so what is your V? So this is your first component, V1. Okay, so divided by the XL 1 So in this case, 40 over pi, so your XL is J omega 1 L. Okay, plus the third harmonic is 40 divided by 3 pi. So 40 divided by 3 pi, and then divided by XL3. So J, this is omega 3, this is your L, so it's J omega 3 L. Okay, so then simplify the equation to get the final answer. So in this case, J can 1 over J is equivalent to minus J, in which it is equal to E negative J pi over 2, or it is equal to negative 90 degree. So that's why you get negative 90 here. Okay, same steps when you have the capacitor inside the circuit. So the XC is equal to 1 over J omega C. So to get IT, you divide VT with XC, in which XC is equal to 1 over J omega N C. So N depending on the frequency at different harmonics number. Let's have another example when you have combinations of R and L in a circuit. So you need to consider the Fourier series of the current IT. Okay, so the VT is given in trigonometric form. So if there's no equation for VT, so you need to derive the equation by referring to the coefficients table. Okay, once you have the equation, then you can develop the Fourier series for the current IT. Okay, so let's start. This is the first equation. So you need to consider the omega. So from the earlier calculation, we know this omega equal to 1000 pi radian per second. So you need to consider the total impedance because you have more than one components inside this circuit. So because VT is equal to IT multiplied with your impedance. So to get IT, it is equal to VT divided by Z. So what is your Z in this case? So your Z is equal to R plus J omega N L. So omega N depending on your first and third harmonic in this case, and L given by 0.1 Henry, and R is 200 ohm. So this is when you have R and L in series. If you have R and L in parallel, so you need to consider the parallel calculation in your step. Okay, so in this case, Z1 equal to R plus J omega 1L. So for the first harmonic, so this is for the first harmonic, omega 1. So 200 is your R plus this is your omega L. Okay, so and then convert this equation into polar form. Next, for Z3, for the third harmonics, so R plus J omega 3L, so your R 200 plus J omega 3, in this case 3000, multiply with L. So you get this equation. So then you can solve for IT. So IT equal to V divided by Z. So in this case you have third harmonics. So the first one, so this is the first harmonic n equal to 1, and you have the third harmonics n equal to 3. So V1 divided by Z1 and plus V3 divided by Z3. So IT for V1, so this is your V1. So divided by your Z1. So this is your Z1. and then V3. So this is your V3 divided by Z3. So then simplify the equation for your final answer. So this one equal to the final equation. Okay, thank you for now. So let's have more examples in the next slides.